be, see, vibration control is a very big thing. Now, what I want to do is, what is a magnetorheological damper? What are these applications, and how we can model it for further analysis? So those aspects I will be touch upon. Now, before that, though this seminar is on, workshop is on electric car, any electric car cannot avoid a suspension system. A good suspension system must make the wheels to be on the road at all driving conditions during hard acceleration, hard braking, heavy cornering, bumps and potholes. It is used to absorb and dampen road shocks by isolating the chassis from the shocks due to bumps. The suspension system must not be soft. If it is too soft, then as there will be too much body roll. Whenever there is a turning or cornering, there is a body roll coming. That means the entire car body try to roll. So if it is soft, then body roll will be high, and also that even for a small bump, it will go up and down quite fast. Okay. While a steeper suspension will make the ride uncomfortable, we can make the suspension stiffer. For example, all the ride comfortable and driving becomes easier if the suspension system is stiffer. That's why you'll find that all the F1 car have a stiffer suspension system. The proper suspension will give good feedback about the car dynamics to the driver. A vehicle handling and dynamics mostly depend on the suspension geometries. Now, what are the components of suspension system? Wheels and tires. Naturally, it provides traction for acceleration, braking, and also absorb bumps, because suspension system contains the wheels, because this can give stiffness and also a little bit of damping. Springs is another component for suspension system. They are present to absorb large bumps, and most commonly used springs are coil spring for light vehicles, but for the trucks and other vehicles it has a leaf spring. Some vehicles also use torsion bars along with the spring to reduce the rolling motion. Dampers. This is a very essential part of a suspension system, and these damper may be passive damper, active damper, semi-active damper. They dampen the motion of the spring after a bump, keep the vehicle from the bouncing excessively. Basically, it's takes away the energy which is being given to the car through the undulation of the road. And there are some linkage mechanism and bearings and bushing to sustain that the entire thing. Now, basically there are three types of suspension system. One, we call it a passive suspension system. Schematic diagrams are shown here. Another one is a active suspension system, and this one is the semi-active suspension system. Now, between these are the suspension system which are placed between the body and the tire. Now, this is the typical suspension system, that is passive suspension system. Let me give a little bit brief outline of all the suspension system. The passive suspension system, those are employed in most of the passenger cars. Major component is the conventional hydraulic shock absorber, which has been shown here. Actually, this is a shock absorber. This is a twin tube shock absorber is shown. These absorbers are filled with oil, and this is the cylinder which has some ports here. Now, whenever the cylinder piston, this is the piston which are there are some ports here. Whenever the piston moves up and down, the oil flows through this. There is some slit here. Okay, so if it goes down, the oil from this one goes on the upper side coming through this slit, and vice versa. Now, in doing so, it gives resistance to the motion of the thing. So one is attached to this is attached to the body maybe, and this is maybe attached to the lower portion as a whole. The energy which is being given to the automobile system is being dissipated. So this is how the shock absorber is given. It's shown in a double wishbone type suspension system, where this is the coil along with the shock absorber. This is the shock absorber. From the passenger's point of view, the ride is fairly compatible, and from the driver's point of view, ride handling is rather robust. Now, next one is the active suspension system. Now, what is an active suspension system? Active suspension is a type of automatic suspensions that controls the vertical movements of the wheels relative to the chassis or the vehicle body with an onboard system. There is an onboard system rather than in passive suspensions where the movement is being determined entirely by the road surface. See, we have no control about the movement of the suspension system in case of a passive suspension system. Whatever road deflection is there, accordingly, the absorber will move. I mean, the shock absorber will move accordingly. Now, active suspension can be generally divided into two classes: pure active suspension system and adaptive or semi-active suspension system. Our topic, today's topic, is mainly on this one. But before that, what is an active suspension system? We should have some idea where it differs from a semi-active suspension system. Now, while adaptive suspension only vary the shock absorber stiffness. See, for example, in a passive suspension system, the properties of the suspension system or the absorber, we don't have any control. Because there is a oil, its viscosity is constant. So whatever stiffness it will give, that is constant for any amount of disturbance. But in case of adaptive suspension system, we can vary the stiffness to match the changing road and dynamic condition. Active suspension system use some type of actuator to raise and lower the chassis independently at each wheel. See, in a active suspension system, there is no shock absorber as such. There is a spring and there is an actuator basically, which controls the movement, up and down movement according to the movement of the road. This technology allows car manufacturers to achieve a greater degree of ride quality and car handling, keeping the tires perpendicular to the road in corners, allowing better traction and control. Onboard computer detects body movement from the sensor throughout the vehicle, and using data calculated by the control technique, control actions of the active and semi-active suspension system are taking places. Now, sorry, active suspension system is available in all the luxury cars such as BMW, Audi, Mercedes-Benz, etc. Now, this is a picture of a active suspension system shown here. Numerous sensors are present which provide information about the road condition, wheel rotation speed, ground clearance, etc. This information is then sent to the engine control unit, ECU. There is an ECU. The ECU process the information and sends the ECU process the information and sends the voltage signal to the active suspension system. Active suspension systems provide a great deal of comfort to the passenger. However, they come up short in terms of vehicle handling. Vehicle handling is sometimes becomes little bit difficult for an active suspension system. Now you see this is a figure of an active suspension system. There are so many sensors attached here, and it's quite complicated. Now, what is a semi-active suspension system? Semi-active system provides better ride comfort than passive system. At the same time, provide better ride handling than active system. In the event the ECU malfunction for the active system, then the active system will fail completely. Semi-active suspension systems are designed in such a way that if any of the above problem occurs, it will revert back to the passive suspension system, because the material within the shock absorber remains. So it will have some stiffness. You cannot change the stiffness, but it will act as a passive suspension system. Thus, semi-active suspension have an added safety feature. This is shown as a semi-active suspension system. There is a solenoid valve which controls. I'll talk about it later with the figure. Now, there is a comparison between semi-active and active suspension system. For semi-active, implementation cost is low. Okay, so this is the basically semi-active suspension system where these damper properties we can change. Lower power consumption, easier to control, very simple design. Design is quite simple because only there is a modification in the damping material and associated thing. Easy to install. Disadvantage, damper constraint. The force range is limited. Performance is not as good as active suspension system. Where is an active suspension system? See, this is the actuator I'm talking about. There is a damper here. Sometimes we put the damper, the spring, and there is an actuator which controls the motion of the spring mass. Okay, as it's receiving signals from the road undulation, so it has a process that thing, and accordingly it will give motion here so that the passenger can feel very comfortable. A wider range of force, no force velocity constraint, can achieve better performance. Power consumption is very high because there is an actuator here which is being forced, the mechanical force is being given actually. Higher weight to power ratio, expensive, very expensive. Major modifications should be made before installing active system into the existing vehicle. Now, since I said that our objective of this seminar is today's lecture is to how to model a passive semi-active suspension system to analyze the motion of a vehicle. Now, how do we model a vehicle? There are a couple of different kind of model we can use. One is called the quarter car model, one is called half car model, and one is called full car model. Now, if you compare this one and this one, you can easily see that this quarter car model is basically a quarter representation, a quarter portion representation of a car. Now, naturally, this is the mass, unsprung mass, and this is the stiffness of the tire and other thing, and this is the shock absorber properties. There is a stiffness properties and there is a damping properties, and this is the mass of the 1/4 of the car which is coming at this tire wheel. Okay, so basically this is, we call it a quarter car model. Now, advantage of quarter car model is very simple. You can design any damper or anything, and you can very easily analyze. What is the disadvantage of this one is that it can analyze only on the vertical direction, though this vertical direction is most important direction from the point of view of the passenger, but vertical movement, but still there are some other movements. For example, if you compare this one and the half car model, now in a half car model you'll see that in a quarter car model, pitching motion, see, whenever a car brakes, now there is a weight shift from front to rear, rear to front, and there will be a pitching motion. So the motion of the front portion will be influenced by the motion of the rear portion and vice versa. So this pitching motion cannot be taken into account in a quarter car model, but in case of a half car model, we can do that. So definitely when we model a car, if you do the analysis with the half car model, then it's better than a quarter car model because you can incorporate the pitching motion. But again, there is a problem with this because there is another motion which is called rolling motion. Whenever the car turns in a corner, there is a rolling motion coming. In other also, suppose one wheel is going on a bump and another wheel is on a straight road, flat road, then also there could be a rolling. Now, that rolling motion you cannot incorporate here, but in case of a full car model, you can do all of them actually. And but number of unknown will be more, the analysis will be more complicated. So this is the way we model a car and try to analyze the thing. And input is giving from here. Input, the road undulation is the basically the input, and output is measured here. Now our objective is to that for a given input, to minimize the output. That means so that passenger can feel comfortable. Now, I talked that semi-active magnetorheological damper. What was my heading of the today's seminar? Is basically a semi-active suspension system damper. Okay. Now, those kind of EMA damper, they usually use magnetorheological fluid. Let us know what is a magnetorheological fluid. EMA fluid, in short we call it, belongs to a class of materials that are known as smart materials. Materials such as, this is another kind of fluid, electrorheological fluid. This is also sometimes we use in a semi-active damper. Now, materials such as air fluid or MR fluid exhibit a change in apparent viscosity when activated by the exposure to an electric charge or by the exposure to the magnetic field. Okay. Now, MR fluids are non-colloidal suspensions of magnetizable particles that are on the order of tens of microns, 20 to 50 microns in diameter. MR fluid is composed of oil, usually mineral or silicon based, and varying percentage of ferrous particles that is coated with an anticoagulant materials. When unactivated, MR fluid displays Newtonian like behavior. MR devices are capable of much higher yield strength when activated. Now, what is the operating principle for a MR fluid? Suppose there is a MR fluid between two plates. Okay, at present, without the application of the magnetic field, they are randomly oriented. Now, with the application of the magnetic field, they will be lined up. Now, applying a magnetic field to the magnetorheological fluid causes particles in fluid to align into a chain. Microparticles are magnetized to produce orderly movement when an external magnetic field is applied. This movement generating finishes when a relatively stable state when a fixed structure is reached. See, this movement, there is a mistake in the sentence. This movement is being come to a stable state. This is a stable state which has come. Okay. After that, there won't be any change in the properties. Now, with the change in when from here to here, when it comes, then there is a change in the stiffness of the material, basically. And what are the components of MR fluid? Liquid carrier, it is the major constituent of MR fluids. 50 to 80% by volume. Commonly used carrier liquids are mineral oils, synthetic oils, and silicon oils. They carry the magnetic particles basically. The magnetic particle size of the magnetic particle is approximate of the order of 1 micrometer to 10 micrometer. As the size of the magnetic particles increases, the attainable force also increases, but the cost of increase of upstate viscosity. There will be increase in upstate viscosity. Additives, highly viscous materials such as grease or other thixotropic additives are used to improve settling stability. Ferrous naphthenate or ferrous oleate can be used as dispersant. So these are the components of EMR fluids. And what is the mode of operation? There are three kinds of operation. Valve mode. In this mode of operation, fluid flows through the two fixed surfaces and magnetic field is applied perpendicular to the direction of the flow. So these are the fixed surfaces. EMR fluid is flowing here and magnetic field is being applied here. The resistance of the fluid can be controlled by controlling the intensity of the magnetic field. So basically what we are doing is we are changing the properties of the magnetic field, and this is an orifice. Okay. So we are changing the properties of the magnetic field, and as a whole, the friction we can increase. So if we can increase friction, then there is a more dissipation of energy. So shock absorber can absorb more forces. This mode of EMR fluid technology is used in various types of dampers and shock absorbers and has fast application in automobile industries. There is another mode of operation which is called shear mode. In this mode, the fluid flows between the surface having relative motion. These surfaces have the relative motions. Okay. In the previous case, these surfaces were fixed, and a magnetic field is applied perpendicular to the direction of the flow. Shear mode of EMR fluid technology is used in various types of brakes and clutches of the vehicle. We can have EMR brakes, EMR clutches also nowadays. So there is one example of EMR brake. This is the rotor, which is fixed to the shaft, and this is some coil attached, and this is the EMR fluid. Okay. Now the EMR brake operates in a direct shear mode, shearing the EMR fluid, filling the gap between the two surfaces, moving with respect to one another. Resistance torque in the EMR brake depends on the viscosity of the EMR fluid. That can be changed by the magnetic field. We can change the magnetic field with the help of this coil. So depending on the strength of the magnetic field, we can change the friction properties between this EMR fluid and the disc. So accordingly, we can braking force we can change basically. There is another application, prosthesis. A microprocessor-based controller determines the current. See, this is the EMR fluid damper which is being used. Now, as the person is walking, the force will be exerted here. So depending on his walking speed and other thing, we can control the EMR fluid friction force so that the person can feel comfortable while walking, because otherwise all this force will be transmitted here and he will be pained basically. So once calibrated to a specific user, the system automatically adapts in real time to the user's walking speeds, stairs or inclination. Accordingly, it can control the motion, okay, so that less force is being transmitted to the body. Sometimes different kind of fixtures also EMR fluid can be used as an aid to fix something. Here is shown a recently been investigated in fixture for holding turbine engine blades while they are being machined. The part to be held is partially submerged in EMR fluid that is contained in a water-cooled electromagnet surrounding the housing. Once the fluid is activated, the side of the housing are moved inward slightly, therefore compressing the activated EMR fluid around the workpiece. Okay, so this is the EMR fluid basically, and this is the part which here the turbine blade is not shown. One part is being immersed in the MR fluid, so that our objective is to hold this thing. So by controlling the MR fluid properties, we can hold it while doing some other work on the part. There are some structural application is also. MR fluid damper are used to control wind-induced vibration in cable-stayed bridges. In fact, wind-induced vibration is a non-linear phenomena. See, as the wind is blown over the cable, it starts vibrating, and this flow in turns, again, it's a sort of negative damping takes place, so that slowly higher amplitude of vibration taking place. In order to reduce this, and Tacoma Bridge collapse was one of the reason of this flow induced vibration. And after that, in fact, that is in 1946 or something, this phenomena of nonlinear vibration, people came to know about this. Now, for any coil, even for electric coil also, this flow-induced vibration can take place. Okay. So in order to reduce that thing, in June 2002, for the first time in Dongting Bridge, became the first cable-stayed bridge to use MR damper to suppress wind and rain-induced vibration. Okay. One of the manufacturer of MR damper is the Lord Corporation, USA. Lord MR fluid damper attached to cable provide a continuously controllable, cost-effective solution to the wind rain-induced cable gallop. We call it a gallop, this large-scale vibration. Okay. Some of the application is household application also we can use. The figure shows the application of MR damper in a washing machine, with the help of which we can control the vibration created during the spinning of the clothes. The problem of semi-active control in appliances such as washing machine is still in its very infancy stage. This work mainly focuses on the vibration induced at high spin velocity. This is the MR damper shown here. Now, lastly, the application in the automobile sector. Magnetorheological fluid dampers are becoming popular in semi-active vehicle suspension application due to their mechanical simplicity, high dynamic range, low power requirements, large force capacity, and robustness. This is the new BMW R1200 shown in the figure, as an additional vibration damper for even smoother running and superior rideability. So this model of BMW motorbike have the MR damper. Now, this is a figure of the MR damper, which generally used in the automobiles. You see that there is a electromagnetic piston inside the MR damper. This is the piston. Okay. And MR fluid valve. This is the MR fluid valve we have talked about. So whenever the piston moves up and down, if it moves down, the fluid from this chamber will go to this chamber through these valves. Okay. And here we actually put the magnetic field, so that if I can put the magnetic field here, the stiffness property and the friction we can increase to a great extent, so that more energy is being dissipated. When a current is passed through the solenoid, in fact, there is a solenoid is attached here, which produces a magnetic field, which will cause the fluid to change in its state from the fluid to semi-fluid or semi-solid state, thereby increasing the damping properties. Now, it was initially developed by Delphi Corporation for General Motors. It allows, together with faster modern computers, changing the stiffness of all wheel suspension independently. Nowadays, with the help of modern computers, stiffness of the all wheel separately we can change it. Okay, because not that the roughness which is coming by all will be different, even for a very smooth road. These dampers are finding increased uses in the US, mostly in more expensive vehicles. EMA dampers are semi-active devices that contains magnetorheological fluids. Besides vehicle suspension system, this type of shock absorber has many applications such as prosthetic. I have said already those things. Even helicopter rotor blade, we can use this magnetorheological damper nowadays to reduce the blade vibration. There are so many type of blade vibration come into place for helicopter. These are the some of the vehicles which use EMA damper. Lamborghini also use this one. Ferrari, they use Chevrolet. Those two are the racing car type of thing. And then Audi, they also use this. And these are the properties of a comparison chart given for EMA fluid and electrorheological fluid. Some of the properties. Any question? Any question?
Hello, Karanjikar sir.
Any question?
No, sir. I think.
Okay. Okay, I'll go on. One minute. I'll
Yes,
go to
sir.
that.
You continue, sir.
Okay. So these are the some of the properties of EMR fluid and electrorheological fluid. Now, what are the research work you can do with the help of EMR damper? First of all, the modeling and analysis of EMR damper, which is very complicated thing, and verify. You have to verify the results with the experiment to analyze a vertical dynamic characteristics of a vehicle, namely displacement, velocity, and acceleration. That means basically the response, road response of a vehicle, and demonstrate the effectiveness of EMA damper governed by, sometimes we use fuzzy logic control to govern the EMA damper. Now, numerical modeling of any damper is very easy to analyze the response of a system. We can use a quarter car model or a half car model or a full car model to see, and we can take some of the typical road response as an input and find out in between the black box. We can put the EMA damper, passive damper, or active damper and see the response, and we can compare the result of a EMA damper vis-a-vis a passive damper. Okay, there have been a number of attempts made to develop a EMA damper model. They can be, this is the mathematical model I am talking about. They can be classified mainly into two different categories: parametric and non-parametric models. Parametric model concerns on physical characteristics such as viscosity and friction, which helps to describe the dynamics of the device. Soft computing techniques such as neural network and fuzzy logic were employed in non-parametric models based on experimental information. Now, this is another aspect nowadays coming. That means here you are doing the some of the mathematical model, but here actually based on the input and output data, you are using the neural network or fuzzy logic. We are using a soft computing technique to model it so that it can match with the experimental result. Now, mathematical model for EMA damper, there are 4-5 type of model have been shown, which are being used by the researcher, and one of them is Bingham model. It consists of a Coulomb friction element. This is the Coulomb friction element placed in parallel with a viscous damper. The viscous damper we have placed. Now, in case of a passive damper, we don't use a Coulomb friction element. Okay, we only use this one. Now here we make a combination of these two to represent the behavior of a magnetorheological damper. Then this is a little bit complicated model, hyperbolic tangent model, where here also you find that there is a viscous damper, Coulomb damper, and there is a spring they have added. And in this case also they have added some uh, uh, viscous damping and spring, so that and they try to match the response of this model with the experimental data. Then there is another one is a dual friction model, and lastly we have Bowen model. This is the I think most used model for AMAT damper, and it can very effectively represents the properties of AMAT damper. Okay, it consists of this these elements. Okay, as shown here, there is a hysterolysis element is there, then viscous element is there, then spring is there. Again, with that, there is another one viscous element and a spring here. So that this is the response input, and we're getting the output here, or the output here. This is X is the input, Y may be the output. Now, in the literature, we found some of the experimental setup made and sinusoidal response data of AMAT damper. They have found out. So I have given some of the glimpses of that thing. A model must be developed that can be accurately reproduce the behavior of the AMAT damper. Now, the load frame shown in the figure, this is the figure, was designed and built for the purpose of obtaining the AMAT damper response data necessary for identification studies. Okay, in this setup, a double-ended hydraulic actuator, this is the hydraulic actuator, was employed to drive the damper. So with the help of this hydraulic actuator, we can drive this damper. Okay, so this is the input to the damper, and this is the output of the damper using the, and this is a force transducer. So we can measure the force, how much force is being transmitted here. And since it is a AMAT damper, so we have a AMAT fluid here. Let us see the using this experimental setup, dynamic response of the damper can be measured for a wide range of prescribed displacement wave forms, including sine, step function, triangle, and pseudo-random. That means the hydraulic actuator might be moving in a sine function, a step function, triangle function, or something. So this is the way it's giving the actuation, and we are find out the dynamic response of the damper at this end. Okay, and what is the formation of the damper? This is the damper basically. Okay, I mean this damper is being, AMAT damper is being shown here. See, the prototype AMAT damper obtained for evaluation is a fixed orifice damper filled with magnetorheological field. So these are the orifice, fixed orifice. There are a number of orifices here around placed in a circle. Okay, and this is the rod which is attached to the actuator. Okay, and this is the magnetic choke, and these are the AMAT fluid. Now when the piston is moving in this direction, fluid from here move in this direction, and if we can control the magnetic flux here, so we can control the friction here. So accordingly, movement of this piston rod we can control. The damper is 21.5 millimeter long in its extended position, and the main cylinder is 3.8 centimeter in diameter. So this cylinder is 3.8 centimeter in diameter, whatever they have done, and 21.5 centimeter long. The main cylinder houses the piston, magnetic circuit, and an accumulator. There is an accumulator here, okay, and AMAT fluid. And the damper has a, I think 10 centimeter stroke, some stroke as shown in the figure. The magnetic field is applied radially perpendicular to the direction of the fluid flow. So here is the magnetic field is being applied, valve type system. Now magnetic field can be varied from 0 to 200 uh, kiloampere per minute for currents of 0 to 1 ampere in the electromagnet coil. Now, effect of changing the magnetic field are readily observed, can be readily observed at 0 volt. When the volt is 0, the emmet damper primarily exhibit the characteristics of a purely viscous device. That means a passive damper, just like a passive damper. That is, the force displacement relationship is approximately elliptical, and the force velocity relationship is nearly linear. Now here are the results shown. See, this is the force versus time response they have shown. This is the force versus displacement. This is the force versus velocity. Okay. This thing, see, you find that the dotted line, this dotted line is a zero velocity, voltage. That means there is no magnetic field is being applied. So it's acting like a passive damper, and this is the force displacement curve for this one, and this is the force displacement, force velocity curve for a passive damper. Now, as we are applying the magnetic field, we find that from the elliptical, it is coming to almost like a square sort of thing. So that force displacement curve and also velocity displacement, force velocity curve, both are changing in nature. Okay. And with the change, they will behave like a Bingham plastic behavior. Okay, that means they are shown the behavior of this one actually. Okay, Bingham model. So in this particular case, experimentally measured force of 2.5 hertz sinusoidal excitation was given with an amplitude of 1.5 centimeter. Now we can change the this hertz 2.5, 4.0, 4.5, and according to amplitude also we can change, and we can get different kind of this kind of results. Okay, so this one actually they have done to show the behavior of the experimental result, that how the damper is been shown response of the damper. Now if I want to model it, how to model it, since it's showing the Bingham plastic behavior, what they have done is they use this kind of model. Okay, to represent that one, and force generated by the Bingham plastic model is given by this one, this equation. If you can, from here actually you can get this equation. Now where C0 is the damping coefficient, Fc is the frictional force which is related to the fluid yield stress, and offset in the force is included to account for the non-zero mean observed in the measured force due to the presence of the accumulator. This is the accumulator. Due to the accumulator, actually there is a non-zero value. See, this is a zero value. Okay, so non-zero value will be observed. Now, and if you see the comparison between predicted and experimentally obtained response for the Bingham model, see the blue color is the experimental result, force versus time, force versus displacement, and force versus velocity. Now you see that both for force versus time, it's fairly matching. Force versus displacement is almost matching, but there is a deviation in the force versus velocity. But this is very important actually. Okay, because damper properties dependent on force versus velocity, which is very important factor. But here there is a mismatch. If we take this model, we find that the model shows this behavior. Okay, whereas actual model is, and there is a hysteresis also here, and this model doesn't show any hysteresis. Okay. Now they have done another Bowen model. I am talking about this. This is the Biowind model. Okay, it's in 1976. The model that is numerically tractable and has been used extensively for modeling hysteresis system is the Biowind model. It is extremely versatile and can exhibit a wide variety of hysteretic behavior. The force in this system is given by this equation. This is the force given by this equation, where C0, K0 and alpha are different constant, which depends on the properties of the damper. And Z is governed by this equation. Okay. So this is a complicated equation. And what is the response? Here you find that post time response is this one. Force displacement response is this one. Here and here, previous one, they are almost matching. But improvement is here actually, you find that. Here we can find that there is a hysteresis, but still it's not matching properly. But that also you can have this control over this one depending on the C0, K0, alpha and those values also. Okay, you can have the control over that. So Bauman model is a better model if you have to model a magnetorheological damper. Now, these parameters of this C0, K0, alpha, those are the parameters of the magnetorheological damper. Now, these parameters of the Bauman model can be changed depending on the external conditions. Keeping these values constant does not guarantee the best performance of the image damper. That means, see, if I can change these properties, if I can change these properties, then the model will be more versatile. Okay, keeping these values constant does not guarantee the best performance of the image damper. This is especially true when the road profile changes continuously. By updating this parameter based on the road condition will allow the image damper to function most efficiently. Variation of this damper can be done through fuzzy logic control. Fuzzy logic is a convenient way to map an input space to an output space. This is the very foundation of the fuzzy logic, and that is great emphasis on the word convenient. Now, so whatever, and this the next phase of work we have done in Jadavpur University. So we have used a Biowind model to model a image damper. Then we give some road inputs and find out the response of the system, considering the mass, unsprung mass, sprung mass, everything for a car. And then we also tried a fuzzy logic controller to use so that we can change the constant parameters of the image damper so that and see how it behaves with a just simple Bauman model. Okay. So this is the fuzzy logic control architecture. Some input is being given and this is the output, and we can find out those parameters for fuzzy logic rule based system. Now we have taken basically a quarter car model where this is the unsprung mass, this is a sprung mass. If we have taken a passive suspension system also, compared this passive suspension system with the image damper and also with the image damper with a fuzzy logic controller. The governing equation for this quarter car model has been I'll call you later. Sorry for the disturbance. The governing equations are given by this one. See, this is the road input, ZR. This is the intermediate input. This is a 2 degree freedom system. you can easily get this equation of motion, and this is the response we are observing actually. And this is the, due to this ZS actually, passenger will feel comfortable or uncomfortable. Our objective is to minimize the value of this ZS, and how fast we can come to rest this ZS depending on the properties of uh, stiffness and the damping of a passive damper. This for a quarter car model, we can easily find out the solution. Okay. Now the next one is the Owen semi-active suspension system. Now there is a spring is there, but still there we can put a Owen model here, which is the basically a magnetorheological damper. And FA, this FA is nothing but this F. Okay, we can find out this value of F at each point if we know C0, K0 and alpha. Okay, so there is a little modification to the passive damper, and the equation of motion will be changed to this one. Okay, this is the governing equation of motion for a quarter car model, 2-degree freedom system, semi-active with the Bowen model. And what is the detail of FA? That can be shown here. This is the governing equations. FA is given by this one. Okay. And alpha, C0, C1, those are the system parameters depending on the damper. Basically, we can find out the values of this one. And this is one damper we have designed, passive suspension system damper, Bowen model. And the third one, we have developed a fuzzy logic control semi-active suspension system, where we are changing the properties of these alpha, C0, C1. We are changing so that it can be more effective. And this membership function for displacement of the sprung mass system is given here. Membership function for velocity of the sprung mass is given here, and membership function for voltage is given. I am not going in detail of the fuzzy logic thing, because that is not the case I am discussing here. Now the parameters we have taken from the open literature. These are the parameters we have taken for a quarter car model. MS is the sprung mass, unsprung mass, spring stiffness, and tire stiffness. These are the value we have taken. Parameter for the Bowen model, that is alpha A, alpha B, C0A, C0B, all these values we have taken from the open literature. And the spring properties also we have taken this. All these properties we have taken here. Okay. These are from the open literature we have taken. And thirdly, what I have given, we have given some road profile. The road profile has a phase delay of 1 second and a height of 0.1 meter. A step road profile we have given here. Okay, that means there is a step rise in the road. Suddenly there is a step rise. How the damper behaves, the three type of damper behaves. Then there is, if there is a pothole, there is a coming down, but we have considered is the ideal case. In actual pothole, we will never get this kind of thing. But and there is a bump road. If there is a bump, we have taken the bump. Okay, so these three road inputs we are given for the three type of dampers, and see how they respond. But before doing anything, we have done certain analysis, but we have to find that whether whatever we have got, whether it is giving correct result or not. So for that we have done a validation analysis to validate the fuzzy logic control semi-active suspension model, the mathematical model represented in reference 24, Talib et al. Will be taken into consideration. Validation will be done for step road profile. He has done only step road profile condition. So whatever we have done is fuzzy logic control MR damper, reference 24, and this is the step road condition. This is a step input of 0.1 displacement given at this time, and this is the response. That means displacement response. We have found that this is the response given by the reference 24. They have found out this one by mathematical analysis, and this is our result, fuzzy logic control adaptive suspension system. This is our response, and if you compare this thing, we find that the nature is almost same, but in our case, we are coming to the zero position faster than this one. Okay, reference 24. This is the displacement function. This is the velocity. We are following the same pattern, but again, the same comment we can get that velocity becoming coming to zero is faster than the reference 24. And this is the acceleration. Only thing is the acceleration. There is a height is little bit more than the reference 24, but again, we are coming faster than them. Okay, the zero position. Then, since our model is more or less validated, what we find that we try to compare all the 4 type of damper for a step road input. So we have given a step road input here. This is the step road input we have been given, and this is the passive response of the passive damper. The blue and red, they are almost overlapping. That is the Barwen damper, that, and this is the fuzzy logic control Barwen damper. Okay, so we find that their response is almost same for a step road input, and this is the displacement given in time. This is the velocity response, passive, Barwen, and fuzzy logic control. This is the velocity has been given, velocity response. Now we find that both these 2 dampers are far better than the passive damper. The response is far better than the passive damper. And a similar observation can be made for the acceleration input output also, acceleration response also. Okay, and this is the response for the bump road profile. If instead of a step road profile, if I give a bump road profile, we get this is the velocity displacement response, and both of them showing the same response almost, the Barwen and the fuzzy logic control, and both of them are better than the passive damper. This is the velocity, and this is the acceleration. Only thing is that initial acceleration is little bit higher than the passive damper. Okay, here only one mistake is that this one is the passive damper, and both Barwen and the fuzzy logic control damper are overlapping on one another. But there is a problem here. In the initial phase, it seems that passive damper is behaving better because less force is being transmitted, acceleration is being transmitted to the passenger. But in the overall, you find that the jerking become reduced faster for this 2 type of damper. And this is a response for the pothole road profile. These 3 conditions we have considered. This is the velocity, the displacement. Similarly, this is the velocity has been shown, and this is the Okay, and acceleration I haven't shown here. Okay, now next, a little bit further work we have done that FLCSAS model analyzed so far did not have any scalar gain. Now we can optimize this scalar gain. Okay, optimization of FL fuzzy logic control damper model is done by tuning these values. Okay, a particular value for a scalar gain is initially assumed and the results are analyzed. Another value is assumed for another scalar gain and the results are analyzed. This way we find out the optimized value of FLCSS model, which is being abbreviated like this, OFLCSAS. Now, this is the scalar gain, usual scalar gain value, and the tuned value we have considered this one, okay, for displacement, velocity, and acceleration 7.2, 6.8, and 10. Now, with the optimized result, here we have compared only without optimization and optimized result. Okay. Now we find that if I use a fuzzy logic control optimized result, we find it's even better than this one. Okay. So optimized displacement variation for step road profile, optimized velocity variation for step road profile, and lastly is the optimized acceleration variation for step road profile. See, all these three cases we find that if we do some optimization analysis, then this is far better than this one. We find that there is too many up and down here, but optimized result giving almost very good result like this. Okay, so passenger will feel uh, more comfortable if we use this kind of optimized damper. Okay. So, and bump profile is also shown here. And the acceleration also shown for the bump road profile. So, what is the conclusion for our analysis is being shown here on all the road profile FLCSS and BWSAS models showed overall better response than the passive suspension system. There was high initial acceleration associated with Bowen model and fuzzy logic control model, and the acceleration profile of Bowen and fuzzy logic control models were rougher than that of the passive suspension system. Now, these are the more or less I have mentioned everything. Only drawback of the optimized fuzzy logic control model is that slightly higher initial acceleration in all the road profiles. After 5 seconds, the acceleration starts to drop rapidly. The semi-active suspension system showed superior result compared to the passive suspension system. So, and you can, if you want to do some future studies on this, on image damper, neural network can be used. A fuzzy logic, fuzzy neural hybrid development can be done for the image damper. Various optimization method can be employed to tune different gain parameters of the model. A more detailed analysis can be conducted by considering different models for the tire and the various unsprung masses such as the wheel hub, axle housing, and differential. Real-time analysis can also be conducted by applying these control methods and optimization technique to a quarter car test rig. You can further analysis the thing with a half car model and a full car model to have a better results, the dynamic characteristics of the models. So thank you. Any question?
Yes, thank you, sir. Thank you very much, sir, for introduction to a new suspension semi-active, that is the MR damper, and discussing the various mathematical model to capture the non-linear property of the MR damper and the various analysis of the suspension system using semi-active or the MR damper. Thank you very much, sir. I open the forum to the all professors and research scholars. If you have any query regarding the suspension system of MR damper, then please ask to the sir. Hello, I'm audible.
Yes.
Hello, Kadam sir, Dinesh Kumar sir, Amol Dhande sir. Hello.
Yes, sir, you are audible.
Yes. Yes, sir. Okay, thank you very much, sir,
Okay. Thank you.
for the new area that you have focused on the modeling of the MR damper. So most of the researchers and the professors may take the advantage of this future scope work and will be they do in their analysis. Thank you, sir. Thank you very much, sir.
Thank you. Thank you.
Have a
Thank
good.
you.
I have pasted the link for the today afternoon session in the chat box. Kindly submit the attendance. Tomorrow morning session is starting with the introduction to the new technologies used in electric vehicle by Dr. Dhamejani, who is a former director of DRDO. So please attend the session at tomorrow morning 10 a.m. Till that, thank you very much. Have a good day.
Thank you.
Thank you. Hello. Okay, sir, you can leave that. You can leave the session. Mohit sir.